In today's hectic world, with its ever-increasing traffic congestion, the intricate mechanisms which regulate vehicle flow are vitally important. This video was produced to help you understand the way traffic detectors work and the best methods of installing, maintaining, and repairing them. Because the information to be presented is so far-ranging, the video has been divided into 4 sections: detector theory, applications, and evolution, detector design, detector installation, and detector maintenance. You may view this video all at once or in several sessions. However, you should first obtain a copy of the Federal Highway Administration's Traffic Detector Handbook, the resource reference for this videotape. The Traffic Detector Handbook is a valuable reference book for exploring a topic further. In addition, there is an accompanying companion manual specifically for this traffic detector videotape. Throughout the video, we will list a variety of installation and maintenance sites. We will discuss detector engineering theories and design criteria, as well as the basics of installation and repair. Our first section covers the basics of how traffic detectors work, their applications, and the ways they have evolved to accommodate modern traffic needs. There are 9 different types of detectors: pressure, push-button, magnetic, magnetometer, inductive loop, radar, sonic, radio frequency, and light emission. Of these, the 2 types of traffic detectors most commonly used today are the inductive loop detectors and the magnetometers. Each of these systems has 3 main components: a roadway sensor, a lead-in cable connecting the sensor at a pull box to the controller cabinet, and an electronic unit in the controller cabinet itself. Over the years, detector equipment has kept pace with modern needs. Early forms of detection, such as sonic, radar, and pressure pads, are still in use and are occasionally installed in special situations. However, as traffic has increased and research progressed, traffic detection has come to rely primarily on inductive loop detectors. This type of detection system consists of 1 or more turns of wire in a saw-cut slot in the street surface at the exact area where the vehicles need to be detected. The ends of the loop are connected by cable to an electronic amplifier, which is usually placed in the controller cabinet. The vehicle passes over the loop and disturbs the loop's magnetic field. This in turn is sensed by the amplifier. Because the loop detector can detect either the presence or passage of a vehicle, it has introduced a new dimension to traffic control. For years, many manufacturers have developed and sold loop detector amplifiers in a variety of sizes, methods of connection, and designs. To overcome the interchangeability problems, NEMA, the National Electrical Manufacturers Association, developed a set of loop detector standards. Now, all loop detector amplifiers must conform to these standards for configuration, mode of operation, output type, crosstalk, and timing. There are 2 detector unit configurations defined by NEMA. The first is the shelf-mounted detector unit, available in both single and multi-channel models. The physical dimensions and the connector requirements of shelf-mounted units are defined by NEMA. The second configuration is the card rack-mounted detector unit. When large numbers of detector amplifiers are needed, the card rack-mounted unit fits into a multiple card rack, requiring less cabinet space. NEMA standards have also been developed for the presence output. A detector unit must be able to sustain a presence output for a minimum of 3 minutes before tuning out the vehicle. Of the 2 types of output, electromechanical relay and solid state is more desirable. Solid-state outputs have no moving parts and are more reliable and more accurate in tracking the actual presence of vehicles. Crosstalk, an electrical coupling that occurs between 2 loop channels, can cause brief, false signals of vehicle detection when no vehicles are there. NEMA standards require some means to prevent crosstalk. such as a frequency selection switch to vary the operating frequency of adjacent loop channels. Today, detectors are used almost every place there are moving vehicles. The most common use of detectors, however, is still on city streets, where most intersections are signalized. These most common detector applications fall into 6 categories: isolated intersection control, arterial intersection control, closed network control, area-wide system control, priority vehicle system control, and pedestrian signal control. Isolated intersection control regulates the flow of traffic without considering the operation of adjacent street signals. Arterial intersection control, or open network, ensures that traffic progresses along a roadway by the display of successive green signals. Closed network control coordinates a network of intersection signals within a defined area, such as a city's central business district. Area-wide system control treats all of the traffic signals within an area as a total system. Individual signals within this area may be controlled by isolated, arterial, or closed network concepts. Priority vehicle system control helps certain vehicles, such as ambulances, fire trucks, and buses, move continuously through busy intersections. Day in and day out, detectors keep more than vehicles moving smoothly. Pedestrian signal control gives people the right-of-way through push buttons and pedestrian signal heads. There are 2 basic types of traffic signal operation: pre-timed and actuated. The pre-timed controller operates in a fixed cycle length with preset time intervals. Intersections with predictable traffic patterns with few variations can use the pre-timed controller successfully. An actuated controller does not set fixed lengths for the signal phases. This controller uses vehicle detectors to assign the right-of-way based on the actual traffic volumes. The semi-actuated controller keeps one street, usually the intersection's main street, in a non-actuated mode. Only the cross street has a detector, because the main street has a uniform flow of traffic and the cross street has low volumes with variable peaks. A fully actuated controller is used at intersections with sporadic traffic distribution. In this case, all of the phases require a detector. The fully actuated controller may allow phases to be skipped, split, overlapped, or interrupted for pedestrian timing. A special class of actuated controller, the volume density controller, provides an even more complex set of criteria for assigning green time. Operating on a continuously variable cycle length, these controllers need accurate traffic information to react in time to varying traffic volume demands. Volume density controllers require specially placed detectors on all approaches. This controller is particularly effective at locations with a heavy traffic demand and high travel speeds. Earlier, we discussed one of the special uses of detectors on city streets: priority vehicle system control. With priority control, the right-of-way must be given automatically to certain vehicles. There are 2 ways of accomplishing this. In preemption, the normal signal sequence is interrupted in deference to the special vehicle, such as an ambulance. In priority operations, the green is held longer for the vehicle, or the timing reverts to green as soon as possible. There are several different types of equipment used to signal a required right-of-way. The most frequently used is the light emitter receiver. The priority vehicle has a transmitter which flashes a high-intensity, high-frequency light code. The intersection controller has optical receivers which read the code and determine what kind of right-of-way the vehicle requires, either preemption or priority. The next detection system used for priority vehicles is the vehicle identification concept. Again, the vehicle has a mounted transmitter to signal the controller. The roadway has a loop to pick up the signal, and the detector unit has a discriminator module. The system recognizes the vehicle and provides preemptive or priority control. The transit vehicle signature loop detector doesn't require transmitter equipment mounted on the vehicle. Instead, this special detector recognizes the vehicle passing over the loop by the unique pulse form of each vehicle. The last type of equipment used for providing vehicle priority is the radio transmitter receiver. Functioning very much like a light emitter system, it uses radio frequency instead of light. Now that we have examined the most common and well-known detector applications, let's discuss several alternatives. For example, traffic detectors can serve an important, highly functional use as a system sensor. Traffic flow information provided by detectors is used by the system to compute signal timing, as well as selecting and developing timing plans. These system sensors sample traffic at strategic locations. The type of sensor used is determined by the type of information needed. To control arterial street systems, traffic detectors need information on volume and occupancy. Inbound and outbound traffic is sampled at free-flowing, mid-block locations. Then the arterial master controller selects a traffic pattern based on this information and keeps the traffic moving. To move traffic efficiently within a network control system, the sensors need to provide data on traffic trends within the network. This traffic information is used along with the time of day, which is provided by a system time clock. Another use of traffic detectors is freeway surveillance and control. In this application, two types of congestion are detected. Recurring congestion, such as rush hour, which happens regularly at the same time and location, and non-recurring congestion, which includes such unpredictable events as a stalled vehicle or an incident. One way to control freeway flow is to control the ramps. Freeway ramps can be regulated through several detection methods, including a pre-timed system, traffic responsive metering, gap acceptance merge control, and integrated ramp control. There is also interest in using traffic detectors for the metering of the through lanes of freeways. So far, this mainline control concept is rarely used in the United States, but it's gaining in acceptance. Mainline control capabilities include driver information, variable speed control, lane closure, mainline metering, and reversible lane control. As we have seen, traffic detectors have many alternative applications. Your traffic detector handbook details the applications mentioned in this video, as well as speed monitoring, traffic counting, vehicle classification, and pedestrian control. Now, let's look at today's detector technology and where it's going. The control and surveillance of traffic is a priority for the 90s, and new technology is a major investment in the United States, Europe, Australia, and Japan. This technology includes new concepts, new products, new applications, and new procedures. Loops have a relatively short life for a variety of reasons. Therefore, we are also looking into substitutes for loop detectors, which are at least as accurate as the loop detector. One such system, the Self-Powered Vehicle Detector, or SPVD, consists of a cylindrical in-road sensor containing a transducer, an RF transmitter with antennas, and a battery. The in-road sensor is powered by an internal battery, and it is connected to the relay by a radio link. The roadside receiver includes a commercially available FM receiver and a tone decoder electronics package. No lead-in or interconnecting cables are needed. This detector can measure vehicle passage, presence, count, and occupancy. Also, two SPVDs placed a predetermined distance apart can measure speed. Another promising emerging detector technology is the video detection system, called VIDS for short. It uses a single video camera with processing hardware and software to provide data similar to that of multiple loop detectors. VIDS can detect traffic at multiple spots within the camera's field of vision. Detection lines across the traffic lanes are inserted on the screen using the keyboard. Every time a vehicle crosses a detection line, a detection signal is generated. Then data is extracted on occupancy, volume, queue lengths, and speed. This technology has been refined to a point that field evaluations are currently being made. The microwave radar detector beams microwave energy toward a section of the roadway from an antenna. When a vehicle passes through the beam, this microwave energy is reflected back to the sensing unit at a different frequency. The detector senses this change in frequency. Although this type of detector has been available for several years, it has been too vulnerable to vandalism to be feasible. However, with new research and better unit designs, microwave radar units are viable alternatives to loop detectors. Ultrasonic detectors operate on the same principle as radar detectors, transmitting a beam of energy and receiving a reflected, altered beam from a vehicle. Not very reliable when first introduced, ultrasonic detectors have advanced in efficiency through continued research and improvements. The last system we'll examine is the infrared detector. One infrared detector producer makes both a passive and an active model. The passive model simply measures vehicle motion. The active model illuminates detection zones with low-power infrared light. This light is reflected from vehicles passing through the zone and focused onto a sensor matrix. Then a processing technique analyzes the signal and determines the presence of a vehicle. This information on vehicle presence can be used for traffic signals, vehicle counting, speed measurement, length assessment, and queue detection information. Another advancement in detector technology is the digital loop test instrument. This device can be applied to testing new loop installations, diagnostics and repair of failed loops, preventive maintenance, and data collection. In the past, detector technology was too complicated to be tested accurately. The digital loop test instrument operates in the ranges necessary to fully diagnose loop detector systems. Traffic detection is a complex, rapidly advancing field. Now that we have an overview of detector theory, applications, and evolution, let's proceed to Section 2 for a look at detector design.